Your phone is buzzing right now because of tungsten. The filament that glowed inside a light bulb for over a century? Tungsten. The drill bit cutting through steel on a factory floor? Tungsten carbide. The armor-piercing rod inside a tank shell? Tungsten. The counterweight in a Formula One car, trimmed to the nearest gram? Tungsten. This metal shows up in places where nothing else survives. It has the highest melting point of any metal on Earth. It's so dense that a block the size of your fist weighs more than you would expect to lift. And it has been doing its quiet, unglamorous work inside the world's hardest jobs for over a century. So what makes tungsten so difficult to destroy? The answer begins in a medieval tin mine with a metal that frustrated miners so much they named it after a wolf. Let's get into it right here on Small Things. Heavier than lead, harder than most steel. Pick up a piece of tungsten and the first thing you notice is the weight. It's denser than lead. A cube of tungsten, the same size as a dice, weighs more than twice what a steel cube of the same size would. That density is not tungsten's only unusual quality. It melts at 3,422 degrees Celsius. Iron melts at 1,538. Tungsten sits between those numbers and the surface of the sun, solid and stable at temperatures that liquefy virtually every other metal. It also resists corrosion, barely reacts with acid, and holds its hardness in conditions that would soften steel in seconds. These properties do not come from a single cause. They come from tungsten's atomic structure and from what engineers have learned to do with it. The metal miners used to curse. It didn't begin as a useful material, it began as a nuisance. In the tin mines of medieval Europe, miners kept encountering a heavy dark mineral mixed in with the ore they were trying to smelt. Whatever this substance was, it interfered with tin extraction, reducing yields and wasting fuel. The miners had no name for it and no use for it, so they called it wolfram, wolf's foam, or wolf's devourer, because they believed it was eating the tin the way a wolf devours prey. The name stuck. It's why tungsten's chemical symbol is W. Scientists began investigating in the 18th century. By 1781, the Swedish chemist Carl Wilhelm Scheele had extracted a yellow compound from it and suspected a new element was hidden inside. 2 years later, Spanish brothers Juan José and Fausto Eluyar reduced that compound using charcoal in a furnace and isolated the metal for the first time. They had freed tungsten, though they still called it wolfram, and much of Europe still does. For most of the following century, the metal sat in scientific curiosity rather than industrial use. Too brittle to work with easily, too hard to shape without specialist knowledge. The world knew tungsten existed, it simply had no practical way to use it. The breakthrough came at the turn of the 20th century through light. Early electric light bulbs burned through carbon filaments that lasted only hours. Inventors everywhere were searching for something that could glow hotter, brighter, and longer. Tungsten was the obvious candidate. It had the highest melting point of any metal, meaning it could run far hotter than carbon without failing. The problem was making it thin enough to work as a wire. Tungsten in bulk form is brittle. Bend it and it cracks. In 1908, an engineer named William Coolidge at General Electric developed a process to work tungsten powder into a wire form, pressing it, heating it, drawing it through dies until a flexible filament emerged. By 1910, tungsten filaments were replacing carbon in bulbs across the world. They lasted longer, burned brighter, and handled the heat without flinching. That single application gave tungsten its industrial footing. Everything that followed, carbide tools, aerospace, electronics, grew from the moment someone figured out how to make this stubborn metal into a wire thin enough to fit inside a glass bulb. Why heat and pressure cannot beat it. So what's actually happening inside tungsten that makes it so resistant? It comes down to atomic bonds and how tightly tungsten atoms hold onto each other. Tungsten sits in a group of metals known for exceptionally strong metallic bonding. The electrons are shared in a way that creates a very stable structure. To pull tungsten atoms apart, to melt the metal, you need to overcome that stability. The energy required is enormous, higher than for any other metal. That's why the melting point is where it is. The same bonding makes tungsten resistant to corrosion. For a chemical reaction to attack the metal, it needs to break into that structure. Most acids and most environmental conditions simply cannot bring enough energy to do it. You can leave a piece of tungsten in the open air for years, and it'll look exactly the same. Iron rusts, copper patinas, tungsten simply sits there. Tungsten also has the lowest coefficient of thermal expansion of any pure metal. In plain terms, when it heats up, it barely changes size. A machine part that expands or contracts significantly with temperature becomes unreliable. A tungsten part stays dimensionally stable even as the temperature around it swings by hundreds of degrees. In aerospace components, in X-ray anodes, in welding electrodes, that stability is worth a great deal. And then there's tungsten carbide. When tungsten combines with carbon at high temperatures, the two form a compound approaching diamond on the hardness scale. Tungsten carbide makes up roughly half of all tungsten used globally. It puts the cutting edge on drill bits, the abrasive on grinding wheels, the wear-resistant tip on tools that shape steel in factories. Without tungsten carbide, modern precision manufacturing would be a considerably slower business. The density has a simpler explanation. Tungsten atoms are simply very heavy, and they pack closely together, weighing almost 19 times as much as an equivalent volume of water. Lead weighs about 11 times as much. Tungsten makes lead feel light. Hard does not mean indestructible. The most common assumption people make about tungsten is that its extreme hardness makes it unbreakable. That's not quite right. Pure tungsten in bulk form is brittle. It doesn't bend before it breaks the way steel does. Strike it with enough force at the wrong angle and it'll fracture, not deform. The same tightly bonded crystalline structure that gives its melting point also makes it resist the plastic deformation that gives steel its toughness under impact. That's why engineers almost never use pure bulk tungsten directly. They use it processed, alloyed, or compounded. As carbide mixed with cobalt as a binder, it becomes not only hard but also tough enough to handle the vibration and shock of industrial cutting. As a heavy alloy, tungsten blended with nickel and iron, it gains the toughness and machinability that pure tungsten lacks while keeping most of its density. As a fine wire drawn through careful heat treatment, it becomes flexible enough to coil inside a light bulb. The brittleness of pure tungsten is not a flaw so much as a constraint that engineers have spent over a century working around. Every application of tungsten is really a story about how humans found a way to harness a property without falling into the trap of the property next to it. The melting point without the brittleness, the hardness without the fracture risk, the density without the unworkability. Where only tungsten will do. Today, you'll find tungsten in places that share one thing in common. The conditions are too extreme for anything else to last. In light bulbs and halogen lamps, the filament still glows at temperatures above 2500 degrees, because tungsten is the only metal that can take that heat without disappearing. Even as incandescent bulbs are phased out in favor of LED technology, tungsten filaments continue in specialist lamps, studio lighting, and industrial heating elements. In TIG welding, a tungsten electrode generates the electric arc that melts other metals. The electrode doesn't melt itself. It simply conducts the enormous heat while remaining solid, which is the only reason the process works. In X-ray machines, high-energy electrons strike a spinning tungsten disk to generate the X-rays. Tungsten absorbs the electron beam, converts it to radiation, and handles the resulting heat, all without softening. Every chest X-ray you have ever had was produced this way. In Formula One cars, small tungsten blocks are bolted precisely into the chassis as ballast. The car's weight must be distributed to within grams of a specific target. Tungsten allows engineers to pack a lot of mass into a very small space, leaving the rest of the car free for aerodynamic shaping. And in the vibration motor inside your phone, a tiny eccentric weight spinning on a motor to create buzz, that weight is often tungsten, heavy enough to produce a strong vibration in an object thin enough to fit in a pocket. The metal that still holds on. So, why is tungsten so hard to destroy? Because its atomic structure demands more energy to disrupt than almost anything in nature will throw at it. The heat that liquefies steel leaves tungsten solid. The acids that corrode iron leave tungsten unchanged. The wear that dulls a steel edge barely touches a tungsten carbide tip. In the places where ordinary metals run out of answers, tungsten is usually the material still standing. Tungsten is not famous because it shines like gold or builds cities like steel. It matters because when heat, pressure, weight, and wear become too extreme for normal materials, tungsten is often the metal that still holds on. The miners who cursed it as a wolf in their tin ore had no idea what they were dealing with. Centuries later, we're still finding new places to put it. If this changed the way you think about the objects doing the hardest work around you, let us know in the comments what you want us to explore next. We might make it our next episode. Thanks for watching. History often hides in the smallest details.